Good morning, we are Team 11, and today we'll go into the analysis and redesign of an electric scooter. Electric scooters are popular last-mile transportation options, typically used in large cities, whether they be personally owned or rented. The market is currently about 100,000 units per year, and our team will be focusing on the rear wheel/motor assembly. This assembly contains 21 parts plus fasteners, and the parts are manufactured using the mill, lathe, injection molding, and other manufacturing processes. Here you can see an exploded view of the rear wheel assembly with each part being labeled to a specific number. Our primary customers are electric scooter rideshare companies such as Lime, Bird, Spin, etc. These companies rent out scooters to customers for short distance transportation and require the product to be extremely durable to last thousands of uses by experienced riders. They also require a compact package to easily transport to and from charging stations. Our secondary customers are the individual consumers who purchase electric scooters to replace bikes, and they are more concerned with the price rather than the long-term durability. Here's our functional analysis, with our main task function being to move the passenger, with our primal basic function of moving the scooter. A few notable basic functions include applying torque and gripping the ground, while notable supporting functions include protecting the motor, absorbing shock, and eliminating noise.
Thanks, Matt. Here's our assembly sequence analysis. The first sequence is our right-to-left method, which starts with the right guard plate on its side and stacks up all sub-assemblies simultaneously, building up to the left guard plate. The second sequence is our inside-out method, which starts by assembling the entire wheel sub-assembly, then the motor sub-assembly, and then encloses both with the guard plates. Using the following criteria, it was determined that assembly sequence 2 is the preferred method because it is much better than assembly sequence 1 for the transferring and handling of sub-assemblies and the testing of sub-assemblies. This is because each sub-assembly is assembled separately as opposed to simultaneously. This is our function component mapping matrix. Along the left side are the 21 different components of the rear wheel assembly. Along the top are the terminal subfunctions from our FAST diagram. Here are some of the notable trends from our function component mapping matrix. The right driven sprocket plate, driven sprocket, and driving sprocket all perform the same 3 functions. The 3 guard plates, as well as the fender, perform most of the same functions. In particular, they protect the motor and help eliminate noise. 12 of the 21 components help to eliminate noise, and 6 of the 21 components help protect the motor. Now I'll pass it off to Chris to talk about the bill of materials.
Here is the bill of materials for the rear drive unit. As previously mentioned, it was assumed that the production volume is 100,000 units. Provided estimation equations and an online estimator were used to calculate the cost per unit breakdown shown here. The total unit cost for the rear drive unit is estimated to be $204. This is a reasonable estimate since the drive unit is the most expensive part of the scooter and represents about 45% of the retail price at $449.
Based on the requirements of the 2 customer groups, different components were separated into platforms and modules. While most components are the same for both groups, some components such as the motor and the gearing are different depending on the needs of each individual customer. One of the largest differentiating options is a different motor. The more powerful motor has the same mounting interface so that the other components can be the same. However, it can provide an increased amount of power for individual buyers who want the choice of faster accelerating scooter.
A key part of the part comparison is the common interference between the motor plate. As you can see, the cutouts in both are the same, so no matter which motor is used, we're able to have that same plate. This also makes it easy to assemble because it's only the same bolts and the same method each time. In addition to the motor, the 2 different sprockets, each matched to their own motor, have the exact same mounting pattern to the rear wheel. This allows for the same mounting to be used and the same rear wheel in both cases. These are the 2 product family assembly charts for assembly sequence number 1 and assembly sequence number 2. As you can see, assembly sequence number 1 introduces the first differentiation at item number 2, while assembly sequence number 2 introduces the variability at number 5. This allows for more commonality in the beginning parts as well as saving on cost.
After conducting manual assembly time estimations and evaluating the necessity of each part, the sprocket plate fasteners, part number 26, and the motor mount spacers, part number 15, were found to add a relatively high assembly time and could be eliminated through redesign. To eliminate the 16 sprocket plate fasteners, the rear wheel hub was selected for redesign. This resulted in the elimination of other parts including the sprocket adapter plates and spacers. Features were also added for easy insertion. With this redesign, there was an overall reduction in mass, part count, and assembly cost. By eliminating the sprocket plates, the durability and therefore longevity of the hub might be reduced. To eliminate the 4 motor spacers, the motor mount was selected for redesign. Locating and easy insertion features were also added for ease of manual assembly. With this redesign, there was an overall reduction in part count and assembly cost. As an added benefit, there is expected to be an increase in durability. With this change, the overall mass is expected to increase slightly. With both of these redesigns, the overall part count was reduced by 25, the assembly time was reduced by 196 seconds, the manual assembly efficiency was improved by 2.2%, and the overall mass and manufacturing cost was also reduced.
Here's the initial DFM for automated assembly. As you can see on the before image, there are the three plates, the left, the right, and the top guard plate, and these were redesigned to just be one bent sheet metal plate. So there's three DFA items that were primarily used for this. DFA 1, reduced part count from the three different plates as well as many fasteners to the one bent sheet metal plate. There's also DFA number 2, which is to reduce fasteners, like I just said, since these different plates no longer need to be joined together. And finally, DFA number 12 prefers the assembly. With the three different plates, they had screws going in both X, Y, and Z. This just allows for one simple placing straight down. As you can see here, there's the two exploded views, one showing before with the three different plates, and the after with the one bent sheet metal plate, as well as reduced fasteners. The overall part count is reduced quite significantly because of this. This is the cost analysis of the DFA study. So as you can see with the old version, the total cost per assembly came out to $116.84 with a combined total of 23 parts. After the initial DFA study was done, the total cost came to $7.50 with a quantity of parts equaling 13. This is a significant reduction in both cost and number of parts, making overall assembly much easier as a result. There are several pros and cons of using this automated assembly DFA. For example, there's much lower automated assembly cost and much simpler assembly. However, due to having the one bent sheet metal plate, there might be possible worse stiffness performance depending on the loads expected. This is easily remedied by thickening the parts or adding a gasket.
The first part that we chose for the process selection was the rear wheel hub. The most critical dimensions are the axle hole diameter, shown in orange, and the mounting hole distances, shown in red. The axle hole diameter is critical since a good fit around the drive shaft will help to absorb some of the shock from the bumps on the road. A tolerance of 0.1 was selected as a standard for free fit holes is 4 thou. The mounting hole distance is critical since the sprocket and wheel must be mounted using these very holes. Incorrect alignment may result in delayed throttle response and inefficient conversion of energy. A tolerance of 0.1 millimeters was also selected. Based on the process capabilities of the rear wheel hub, either die casting or injection molding would be the ideal processes. If we wanted a metal wheel hub, die casting would have been selected. However, we decided to go with a thermoplastic. Therefore, the injection molding process was selected instead. The second part that we chose for process selection was the motor enclosure. The most critical dimension is the distance between the mounting holes, shown in red. This distance is key for correctly mounting and protecting the motor since the motor will experience extreme vibrations when spinning. A tolerance of 0.1 was again selected. Based on the process capabilities, either machining or sheet metal working should be selected. Machining the enclosure out of a solid billet of aluminum would provide the most structural strength, but would require several machining operations to complete. This is why the sheet metal working process was selected instead. All of the holes can be stamped out in a single motion, and the two bends can be made to form the shape of the motor enclosure.
Thanks, Matt. Here's our DFM work for the wheel hub. We first estimated the manufacturing cost of the wheel hub by using the following injection molding cost equation. After performing this cost estimation, we used DFM Pro to further analyze our redesign and determine if there were any other changes we could make. DFM Pro suggested that we create uniform wall thicknesses, add draft angles to protruding surfaces, and decrease the rib thickness. Prior to any redesigns, the cost per part of the wheel hub was $13.32. After our initial redesigns, the cost dropped drastically to $1.37. And after the DFM Pro redesigns, the cost decreased another cent due to a smaller material cost. Now I'll pass it off to Chris to talk about our DFM work on the wheel enclosure.
The wheel enclosure was redesigned to allow for use of sheet metal forming rather than machining. Several changes were made, including removing certain poorly shaped holes to allow for only standard punches to be needed. Additionally, all corners were rounded, and holes were moved away from bending surfaces. These changes, as well as the switch from machining to sheet metal, reduced the part cost from $6 to just under $2. Additionally, this allows for a single piece rather than the need to assemble parts later on. This product can be combined with a service by offering an electric scooter sharing service. This way, consumers can rent scooters rather than buying them, saving them money and saving them on the major upfront cost of the purchase. Additionally, this means that they have better access because scooters are more available when they need them, and it benefits the environment because scooters are used more often and people are more likely to use the product. Overall, the design changes were extremely successful in reducing the assembly time and overall cost. Part count went down, assembly became easier, and the number of fasteners also decreased. A few negatives included a slight decrease in stiffness due to using sheet metal rather than machine parts and higher tooling cost. However, the overall cost was significantly less at over $16 less per unit or $1.6 million over the entire 100,000 unit batch size. In the future, we'd like to looking instead at mounting things directly to the frame